with some of our products. There's a couple of things we'll cover with this. I want to talk a little bit about the linear shaft motor, magnetic counterbalance, some micro direct drive motors, and some customized control platforms. And just tie it into how we may have solved a problem specifically for a customer related to a challenge they may have had. So it's more about solving the customer's problems and the specific individual components, but it's, it gives you a flavor of what we like to do in terms of how we sell our products. So to start with linear shaft motor, I'm pretty sure most of you are familiar with our linear shaft motor product. I know Sasha's a big proponent of this solution. Simple, non-contact, high precision is kind of our tagline around this. Why is it simple? Well, it's really pretty straightforward. You got a stainless steel tube, you got magnets embedded in the tube, north to north, south to south. Gives us very good high flux production. And then we wrap coils around in a forcer that moves back and forth along the shaft. So a couple of the key things that make this really powerful is it's a coreless design. So there's no iron, which means there's no preferred position. So the magnet, so there's no cogging, very smooth motion. Again, being an ironless design, there's no eddy currents generated. So the system is, the forcer is very low heating in terms of, there's less heating in the system. What else makes it simple? Well, it's a non-critical air gap. So I don't care if that shaft is perfectly centered in that air gap of the forcer, just as long as it's not touching the sides, because then that just generates some wear. And since this is really non-contact, you really don't need that. So having that shaft in perfectly centered is not an actual requirement. So it makes it easier from a mechanical design to build the supports and deal with making sure you've got clean, smooth motion. And then, of course, it's a three-phase BLDC motor. So it's really, from our perspective, it's drive agnostic. It's compatible with any of the major conventional brushless drivers. We use all sorts of, we've used Panasonic, we've used Arcus, we've used, I've had one of these on a Morgan, of course. I think my preference in the long run, and you guys rep these guys, is the Copley drives. We've had some really interesting applications and success with the Copley drive. So it's capable of being used in many applications alongside some of the other mainstream products. So I'm going to touch on kind of the innovation number one that I would call it. It's not a huge innovation in terms of this has been around, but utilizing the magnetic structure in the forcer and the shaft and integrating analog Hall sensors at 90 degrees to basically mimic a sine cosine encoder, 1 volt peak to peak with a 2.5 volt offset, and then interpolating that signal through either the drive's capability, which like the Copley or some of the other drives have the ability to take that sine cosine, split it up into many pulses and create fairly high resolution. Or we have an option where we provide a integral interpolation circuit either within the forcer itself or within the connectorization of the feedback device into the driver, so that you could supply the conventional incremental signal into the drive. Now, what we've been able to do, because of the pulse pitch of the motor and how the interpolation rate, we can get down to really sub-micron resolutions, typically about 1 to 3 microns, but we've seen it with a 16-bit interpolator down to below 1 micron. in terms of repeatability. So it's real important to think of this. It's very repeatable, but due to the variation in the size of the magnets, there's some tolerancing. Then when you think about exact spatial positioning, it's not as accurate as you would have with a conventional linear scale. So it really is an application-dependent solution where you have situations where you're making quick point-to-point moves and need repeatability. They're perfect for it. If you're trying to do a very precise positioning where spatial positioning is critical, then it's got higher resolution or much higher tolerance around that than with the repeatability. But the key here is it eliminates the need for an expensive linear encoder, and it also eliminates the need for an externally mounted encoder device. So it makes it simple again, back to the simple concept. So where do we use this? In a number of different applications. So what is this? This looks like, to me, it's 12 by 8, so it's a 96 well plate used in pipetting applications, life sciences. So 96 well plates, a common plate. There's higher density ones, there's lower density ones. But in this particular one, those centers of the circle are 9mm pitch. So how do you create a system that can have multiple heads on it to meet that 9mm pitch? So we took our team in Japan, kind of thought through this, and certainly one way is, can you make a motor that gives you the 9mm pitch without doing anything else? But in order to get the forces required and such, getting that small in terms of a motor, the forcer itself, became a challenge. So they took a kind of an innovative thought pattern on this, is to take these motors and offset them in a way that still gives you the 9mm pitch, but you still have the capability to use the motor that's bigger than the 9mm. So this was a unique system that we created. And the other thing that helped in this is using the integrated analog Hall sensors. So now you have your linear shaft motor, your analog Hall sensors. This one has spring-loaded counterbalance in this particular design that we came up with. And we also used, one of the things you also have to be concerned with that close proximity of motors with the magnets, any stray magnetic field that would interfere with the motor directly next to it. So we also came up with a solution with using a magnetic shielding plate, which would prevent the magnetic interference between shafts. So this was a cool little thing that we built, and it wasn't something actually we could sell this as a product altogether, but really it was really to show and give customers the idea of, hey, you could consider something like this to make us something work for you. And let's see, so this shows this in motion. So you've got 8 axes of independent motion that you can control, vertical axis on a 9mm pitch. So that's this brief video of that. Before I keep going through here without listening to you all, is there any questions or comments on that first portion there? So I'll keep rolling.
Yeah, I think you're good.
Okay, so let's talk about the next kind of topic here is counterbalance. Now, in the last one I mentioned, we talked about spring counterbalance, but oops, sorry, I'm gonna push it over. So why counterbalance? Of course, you're all aware. Any vertical axis that's back drivable or free moving requires either some type of brake or counterbalance. If you lose power and it falls, it could be detrimental to a device that may be underneath it. So there are a lot of different types of counterbalances. You have magnetic, you have spring, you have air, and then this YouTube video is, I think, yeah, here we go. Shows you the more conventional approach. So that's a vertical axis moving up and down, and you can see there's maybe some wires coming up from that, and it's going up, and as the video progresses, you'll see it in the back. There's just a big weight. So, almost kind of like you see on an elevator where you have this big counterbalance that moves up and down with the elevator. So that's the classical approach. But there's also air. So you got the pneumatics, which tends to be a little bit more complex for setting up. It's noisy. You got other components you got to worry about. Also, I guess you could throw in this hydraulic, which also has a lot of other elements that come into play. It makes it way too expensive to try to do it that way. Spring method is also viable, but springs are, notorious for compliance issues, and that makes tuning drives very challenging because of all the compliance associated with the spring as you expand it and contract it. Eventually, the fatigue of the spring will wear it out or reduce its spring coefficient. And then magnetic. Now, magnetic's been around for a while as well. Linmont probably you're familiar with has a fairly nice magnetic design, but it is a little bit big, and it also has stray magnetic fields that can interfere with some sensitive equipment. So we've come up with a next slide, please. We came up with a new magnetic counterbalance concept that is quite unique in terms of how our approach to solving this. Again, this was done with our R&D team at the NPM Techno Center in Japan. And so we created a stator that has magnets. Magnets are loaded down into it vertically, and they're positioned in a very specific way. And that's part of the secret sauce of the design. And then we have a hybrid shaft. We have a non-iron and an iron shaft. And what that does is it creates a preferred position of that rod, the total rod, based on the force generated through the magnetic circuit of that system. So it's a very simple solution. It's a stator and a hybrid rod, and that's it. And you support it on both ends, maybe put some type of bearing in there. There's an air gap in there, so that controls, and you can see the force per position is very constant. And so having that force being constant starts to make it much easier to do tuning, and eliminates some of the compliance issues. And we found this to be quite successful with some applications we've worked with. We call it the G-less or gravity-less solution. The other thing about this design is because the iron shaft and the non-iron shaft are not magnetic, they're not magnetized. You don't have any stray flux from that. And the way the stator has the magnets positioned, there is very little, almost no stray flux from that portion of the body as well. So that means you can get much tighter positioning in your mechanics, like in this example where it's very close to the forcer itself and the actual shaft or linear shaft motor. And it makes for a nice, compact, small package in these vertical applications.
I've got a quick question.
Sure.
Now, when you have this counterbalance, is it dependent on whether or not you're flying the forcer or the shaft?
Either way,
Okay.
that would be in terms of magnetically how it's set up. I mean, mechanically how it's set up. But yeah, it doesn't matter if you're flying the shaft or the forcer. You instead of, like in this case, we're flying the shaft, so it's connected to the shaft, moving with the shaft. But you could just as easily, if the forcer were moving, was in some fashion connected into that with the moving element.
Mhm.
And so the key on this one is then, okay, you need to understand what your weight is that you need to offset. And so, there's a couple of things with this system that you can do. Is one is, first of all, if you have enough force, if you have more than enough force to hold the unit in an up position, then if you lose power, the system will actually move up to the top. So it'll move up position instead of falling down. If you have more force in the counterbalance, then you have weight to overcome. But you could trim that, so you could add weight to your moving element in some fashion, to get it to where it's closer to even, so that if you have power outage, it would just sit where it's at. But
So,
so you want it to sit where it's at or move up.
so each one of these counterbalances is custom made for the application?
Well, there's a couple of different versions that give you a specific force. So there's like a different family. There's a 8 millimeter, 13 millimeter, 16 millimeter diameter stator, and those give you different forces. But then the question is, do you actually trim out on your axis depending on your actual load weight? So each one you would need to match your counterbalance weight in some fashion. Or if you didn't, if you had more counterbalance than you needed, it would take the unit up and not let it fall down. So if allowing it to move to an up position is not an issue, then it doesn't necessarily have to be trimmed for every application. But just like a conventional counterbalance, where you want to try to match the weight as close as possible to the load weight.
Okay, thank you.
Mhm. And I think, as this is a brand new product, as we get into a number of applications, I think there's going to be things that we're going to have to consider on our side to help make that part of it easier. Because you can change the diameter of the iron shaft, make it slightly smaller, increase your air gap, and get less force that way. So there are all sorts of little things that you can do, but we need to figure out how to make it easy from the application perspective, um, to solve that problem. So these are the different sizes. So we have 2.2 newtons and 5 newtons and 16 newtons of counter force. Right now the stroke is at 40 millimeters. So the stroke on these right now is limited at 40 millimeters, but we're working on a longer stroke length, probably closer to 90 or 100 millimeters. And they come in different, like I said, 13, 18, and 26 is the diameter of the stators. And I don't know if this video is going to work. We'll try it. Let's see if it does. It starts out, but then it gets into a fail mode. So, okay. We'll continue on, and I'll come back to this one. I can come back to this one. So anyway, the summary of this is, of course, counterbalance. The basic advantages, or you can prevent valuable fragile tool pieces and workspace from dropping. It's not, in this case, it's non-contact. There's no wear, there's no maintenance, as opposed to some of the other solutions that do have maintenance and are noisier or have other wear issues. There's no flux leakage, so you can assemble these closer than some of the competitive designs that are out there to save space, and it's very stable force in any position, so it helps simplify the tuning process, and we get some really good dynamic response. So we've been working with this on a couple of applications on a linear Z-axis on a gantry system using the linear. So it was I think it was an 8mm linear shaft motor and a 16mm counterbalance using for a sonic sensor that's using an ultrasonic inspection machine. And we've just been working with them on this to prove out some of the concept, and it's working really well. We're doing some other things with it, but combine this with the analog halls, and you've got a nice compact package for vertical axis. So that was the second kind of sort of innovative solutioning that we've come up with on some applications. The next one I wanted to talk about real quick is our micro direct drive motors. Our partner in Japan, these are some of the world's smallest direct drive servo motors. Go from 13mm to 100mm diameter with through-hole design, pretty lightweight and precise. A pretty powerful combination for certain applications in this. So, of course, I mean, I'm sure you guys in motion are familiar with a lot of different reasons why direct drive is a good solution to eliminate compliance and make things more robust. But, so that's the benefit of direct drives. You have all these, they're quiet, no backlash, no compliance, reduced parts counts, no maintenance, robust application. And I dropped into the AI. I said, tell me what are the benefits of direct drive, and those are the kind of things that this was the answers. And so all those things that we talked about, this is what comes up. And kind of the funny thing was when this came up and I started looking at the references that they go to. They go back to some of the things I wrote on the direct drive motors that I was familiar with Cole Morgan back in a few years ago. So this is the kind of thing that we see on why that's important. So these are the smaller elements, 13mm diameter, pretty small, up to 100mm in diameter. The larger ones also have the options for through holes, and we can get up to 3,000 milliNewton-meters in continuous torque, absolute or incremental encoders. And again, these are designed for direct drive applications, typically higher torque, lower speeds. Of course, the smaller ones, they can run up higher speeds. And the last thing about this product is we have a lot of different customizations or variations that we can play with this on. So we have, as I mentioned, both incremental and absolute encoders, through-hole or shafted designs. We've had an application where we actually mounted a short actuator screw into the direct drive motor, mounted to the shaft to create a very short stroke linear actuator. We can connect it with harmonic drive gearboxes or other types of gearboxes. We can do custom magnetization, different mounting preferences. It's a really nice motor. It's very well built. It's a little pricey from thinking of typical small motors, but it's got some really good capabilities. Some of the application and markets that these are used in is vision systems and gimbals, haptics, where you're got something where you're using it in a remote situation and you want to feel something when it's encountering some torque and a very quick response back allows that in some of those applications, medical devices, good in some semiconductor applications, so wafer spinners for inspection, very, very tight tolerance instead of a flatness. Used in medical, life science, and robotics applications. This is just a short video shown on an inspection machine that's spinning a PC board that's getting images taken at a variety of angles, and then those images are then used to inspect and determine if there's any faults in the PC boards. And then the last element I wanted to talk about real quick is our custom control capabilities. I know you guys represent some of the other drives and systems, but one of the things we have the ability to do is to do custom boards. And using we call our hybrid commander core motion controller. So that silver item that's plugged into that PC board is our commander core. It's a 4-axis motion controller with full capabilities of interpolation, linear, circular, helical interpolation, very fast, very good for a lot of different motion applications, many motion applications. And we can plug this into a custom PCB and then you include other drivers, interconnections, and to simplify applications for customers that want to reduce the space in cabinets or have a need for a very custom solution. This was a particular customer that had been using our product, used the Arcus Titan drivers, box drivers in a cabinet. The first time we dropped in the development board, so that white board that you saw in the previous picture and in this picture is our development board. So the development board allows you to do complete experimentation and development of a system, so you can determine exactly what you may need in terms of what your final PCB may want to be. And then the after picture then shows we redesigned this with a custom PCB with 3 Titan cores on the device, the commander unit, and simplified their cabinet, reduced their labor by somewhere in the neighborhood of 30%, reduced the cabinet space by about almost 50% in terms of overall volume. And it really was very successful for them in that application. And when you think about custom PCBs, we have the capability, because we have a library of building blocks that we can use to, power stage, drivers, how we can deal with I/O, and a few other things that we can plug into our models, like kind of almost like Lego blocks, to build out a custom PCB, and we can do it very fast. And certainly when we do custom, there's some development costs that go along with that, but they're very low, very reasonable in terms of what you would think a custom PCB would take. We can spin these up pretty quickly. We had an application that required a new simplified 3-axis controller for linear steppers, and we were able to come up with a design, spin the board up, and get first prototypes out in 4 weeks for the customer that was in a kind of a rush situation. They were able to test it. Most of it worked. Of course, you expect there's going to be some possible issues, and we went through the second pass to finalize it and clean it up, and that was very successful for us. We're now in a redesign to actually add a 4th axis to that board. The other thing that we can do is, remember I talked about the linear shaft motors, I talked about being drive agnostic. In this case, same thing. We can take, you know, and right now we're working with Copley on how we might use, you know, like the Nano or some of their new kind of board level drivers to drop here instead of using the Arcus Titan cores. So we're looking at that, and of course we've used some others like Elmo and some of the other ones that are out there. But you know, again, my preference is been favoring more and more of the Copley because of some of the capabilities we've seen with it in some applications we've worked with it recently. So I think that's it. So questions on anything?
It doesn't look like it.
If you're trying to ask a question and you're muted, then we can't hear you. But yeah, I mean, if there's any other questions about NPM or what we do or anything, just, you know, I don't want to take up any more of your time because I know your time is extremely valuable. So that's why I don't like to drone on things. But if there are other questions, please, you know, just let me know or shoot me an email.
I guess just from a marketing perspective, what's the general lead time for most of the products?
Okay, so linear shaft motors typically were maybe a 6 to 8 week kind of lead time. We've been able to get them in shorter than that in rush situations or when customers lose their previous motors we sent them. And the micro direct drives, they're again around I would say a 8 week kind of lead time, but again, we've been able to, we had a customer out on the East Coast, we shipped in 2 weeks. So it's always, you know, the typical lead times that we're seeing is in the 6 to 8 week lead times on most products, other than maybe some of the stepper products that are out 4 or 5 months because of supply chain things that go along with those. But for these products, turnaround is pretty quick. And in certain circumstances, we can improve delivery by checking through and seeing if we can squeeze something ahead of something else. Or sometimes they do have stock built up in some things. So.
And real quick, in some situations with the shaft.
Yeah, Mason, you're cutting in and out there.
No? Hey, can you hear me now?
Yeah. Now
Yes.
Sorry about that. Say there's a lot of benefit in your shaft motor on length.
Yeah, you're still cutting in and out. It's like I hear the first part of the word, then you go away.
We got wind.
Hey everyone, it looks like we may have lost Mason. If there are no other questions right now, Robert, if you have any closing comments, I think otherwise we can call this meeting.
Sure. Yeah, I just want to say I wanted to thank everyone for their time this morning. This was a pretty good group, and if there's any other topics in the future that you guys have questions about, maybe related to some of the stuff we do, I'm more than happy to spend some time with you. And if there's any other questions that you have, just get in touch with us. We're happy to help support you in any way we can.
Well, we appreciate your time this morning, Robert. Thanks for this overview for Nippon Pulse products. And for all attendees, just reach out to your Western Automation rep if you want to engage more on that product. Other than that, have a great week, everyone.
Thank you.
Chris, yeah, my internet was in and
No worries.
Thank you guys. Appreciate it.
Thank you.
Thanks.